This is the second of 3 lectures from Chapter 15, all about acids and bases. The first lecture talked about how to identify an acid and base, how to identify conjugate acid-base pairs, and simple calculations of pH and pOH. This section will talk about how to evaluate the strength of an acid and base. First thing is the definition of a strong acid or a weak acid, and a strong base or a weak base. A strong acid or strong base simply means that that substance ionizes 100% in water. So for example, if you look at hydrochloric acid, which is a strong acid, and you put it in water, whoops, I meant H2O, 100% of it will exist in the ionized form. There'll be none of the intact original acid. That is the definition of a strong acid or base. Strong acids and bases are also strong electrolytes. If you remember, an electrolyte is simply something that conducts electricity. In order for an aqueous solution to conduct electricity, it must contain ions. So of course, a strong acid or strong base in aqueous solution also strongly conducts electricity, is a strong electrolyte. There are 6 strong acids. You need to have them memorized. And the nice thing about that is every other acid in the entire world compared to these 6 is weak. I think I mentioned these in the last lecture too. So I guess you probably can intuit by now that a weak acid is an acid that does not exist completely in the ionized form in water. A strong base also ionizes 100% in water, but basically what it does is the strong bases all have hydroxides attached to them. I think you know from me mentioning, hopefully, that nitrogen-containing compounds also are bases, but they are all weak bases. So the strong bases all have hydroxides as part of them. And so in solution, a strong base will exist again 100% ion form. So the bases, the strong bases that you need to memorize, they are all made with group 1 metals, lithium, sodium, potassium, etc., cesium, combined with a hydroxide. Those are all strong bases. And then the heavy group 2 metals, those are the alkaline earth metals, calcium, strontium, barium. The alkaline earth metals that are higher up in group 2 on the periodic table, for example, magnesium hydroxide, are weak bases. So let's talk about weak acids and bases for a bit. A weak acid or base is one that does not ionize completely in water. In fact, only a very, very small portion of a solution containing a weak base will ionize. So, for example, hydrogen fluoride, when put in water, hydrofluoric acid, is a weak acid. It's the only halide acid that is weak. And so since it's weak, when you put it in water, most of the molecules will remain intact as hydrofluoric acid, and only a very few of them will ionize into the fluoride ion and hydronium ion. And as a matter of fact, if you start with 100 HF molecules and put it in water, less than 1 out of those 100 will actually ionize. And greater than 99 out of 100 will remain intact. So weak acids, there's quite a huge difference between weak and strong acids and weak and strong bases. There are trends that make an acid stronger or weaker, and so we're going to look at these trends with respect to the periodic table. So as you move left to right, and this would be a multiple choice type question. As you move left to right across a period on the periodic table, acidity increases, okay? So hydrofluoric acid is more acidic, is a stronger acid than water, for example. And water, of course, is a stronger acid than ammonia, okay? So going from nitrogen to oxygen to fluoride, acidity increases. And that is due to the electronegativity of the atom that the hydrogen is attached to. Remember, in order to be acidic at all, a hydrogen has to be attached directly to an electronegative atom. And so the more electronegative atom it is, the more acidic it will be. So if you go down to the next row, row 3, hydrochloric acid, of course, is more acidic than hydrosulfuric acid. Now, there's a different type of trend going from the top to bottom down a group on the periodic table. In this case, even though electronegativity is decreasing going down, the acidity increases. So the important trend going down has to do with bond strength. The important trend going left to right has to do with electronegativity. So let's look for a minute at what an acid does when it behaves like an acid. So I'm going to write some generic acid here. And we're going to put it in water. And a certain amount of it is going to ionize. Okay. So to make this, to act as an acid, we have to break the bond between the hydrogen ion and the electronegative atom it's attached to. So two things have to be true to be a strong acid. The bond between the hydrogen and the electronegative atom must be relatively weak. Okay, otherwise it's not going to want to break. And two, the anion formed from the electronegative atom, so that would be A minus in this reaction, must be stable. Okay, so the trend left to right across a period has to do with electronegativity and the stability of the anion that's formed. The more electronegative this is, the more stable the anion is. Electronegativity means attraction to extra electrons, and so obviously the more electronegative something is, the better it can handle that negative charge. And obviously the weaker the bond is between hydrogen and the electronegative atom, the easier that's going to be able to break and the more acidic it will be. And so that's why going top to bottom down a group, acidity increases, because the bonds are easier to break as you go top to bottom. Why would the bonds be easier to break at the bottom? Okay, so it's lower bond strength or weaker bonds. Why would that be at the bottom of the periodic table? And that's simply to do with size. Okay, if you have two atoms and they're both small and they're bonded together, they can get very close together and have very strong attraction. If you, on the other hand, have two large atoms, okay, they're actually pretty far apart, and the attraction between them is not as strong. I always use the analogy of people. If you have two very small people, they can get real close to each other and hug. If you have two very, very large people, they may not even be able to get their arms around each other. So their bond is probably not quite as strong. So that explains the acidity increasing down a group. And a final trend, a third and final trend with acids, and that's not with binary acids, but when you have more than two atoms in an acid, those are typically called oxyacids. They have oxygen in them. The more oxygen you have in that molecule, the stronger the acid or the more acidic. So Chloric acid, for example, with 3 oxygen is more acidic than chlorous acid, which is more acidic than hypochlorous acid. Alrighty, so that's just a table, another way of looking at what I said. I wanted to stick in your head a little bit more. So if you were to look at this table and I were to ask you what is the strongest acid, pretend like this column wasn't there, how would you figure that out? Well, the strongest acid is going to be the one with the weakest bond energy. Because remember, you want to break that bond in order to be a good acid. So it has the weakest bond energy. So how do chemists measure the strength of an acid or a base? Typically, it's with the equilibrium constant K. So if you have a weak acid or a weak base, it exists in equilibrium with the ionized form. Okay? If you have a strong acid or a base, there is no equilibrium. 100% of that acid, if it's a strong acid, will ionize into the hydronium ion and the anion. So there's no reversible reaction. The beginning stuff is gone, and all you have is the ionized form. So we're only going to talk about equilibrium constants with weak acids and bases. So I should have put a subtitle up here. Weak acids and bases. They're the only ones that have an equilibrium, the only one that have a K equilibrium constant value. So what value of K, what magnitude of K means a strong acid? Well, if you have a lot of the ionized form, that means you have a strong acid or strong base. Okay? So that means if you have a lot of product, it's going to be a strong acid or base. The bottom line is a lot of product means a large equilibrium constant. So the stronger the original acid or base, whoops, I didn't mean to start marking that. The stronger the acid or base, the larger the value of K. Don't worry about this last sentence yet. We're not there yet. All right, so to give you a specific example, hydrocyanic acid is a weak acid. It's not one of the 6 strong ones that you memorize, and so here's its equilibrium. A weak base, methylamine, again, it's in equilibrium because it's not one of the 6 strong bases. Strong acids and bases like hydrochloric acid or sodium hydroxide, the original molecule is gone. They ionize 100%, and so there is no equilibrium. So take a look at this table, and I mainly want you to look at equilibrium values. These are all acids, and so the equilibrium constant is called Ka, and you will notice later on we also have a Kb, which is the equilibrium that weak bases have in water. So remember what I just said in the last slide. The larger the Ka, the stronger the acid. So what is the strongest acid on this table? Well, the largest Ka value is that, all right? And what is that? Chlorous acid. What is the weakest acid in this table? And that is, let's see if I can move that up. There we go. 1.3 times 10 to the minus 10 is the Ka value, something called phenol. It's basically an OH group. So alcohols are really not, they can act as an acid, but they're very, very weak acids. So a typical multiple choice might ask you, would you expect the equilibrium constant for the reaction shown to be less than 1 or greater than 1? How on earth would you determine that? Well, if it's a Ka value, you know you've memorized your 6 strong acids. Is this one of them? No, that is a weak acid. Therefore, almost probably less than 1% of it ionizes. And so K is much less than 1 for any weak acid. Here we go now with that sentence I told you to ignore a couple slides back. The weaker an acid is, the stronger of a base its conjugate base is. So let's look at our generic reaction for an acid again. We're going to dump a weak acid, I'm going to just call it HA, into water. There's going to be an equilibrium because it's a weak acid. And here are the ionized products. And let's see, the weaker the acid, that means not very much of this is formed, the stronger the conjugate base. So here's the conjugate base of the original weak acid. So all that's saying is if it's a very weak acid, this forward reaction is not very likely to occur. And what that means, if the forward reaction is not very likely to occur, that means that the reverse reaction is favored, okay? And if the reverse reaction is favored, that means the conjugate base likes to react. In other words, it's strong. So you may need to kind of sit and read through that and make sure you understand this yourself. But it is a relatively important concept. Calculations for K, the equilibrium constant, Ka and Kb, are similar to the calculations we've done for pH and pOH. So I told you in the last lecture that this little p simply means minus log of something. So pK is minus log of the Ka or Kb value. And so if you're given a Ka and asked to calculate pKa, you simply take the negative log of it, just like you did with pH. And similar, if you're given the pKa of something and asked to calculate Ka, Ka equals 10 raised to the minus pKa. And very similar to pH, the stronger the acid, which means the larger the Ka value, stronger acids have larger Ka values, and also have smaller pKa values, very similar to talking about acid and pH. So we talked about calculating simple pH problems in the first lecture, and just to kind of give you a reminder, what is the pH of a 0.050 molar solution hydrochloric acid? Get in the habit of asking yourself what type of acid or base the problem is talking about, if it's strong or weak. This is strong, okay? So calculating the pH of a strong acid or base is really simple because 100% of that molarity gets converted to hydronium ion. So whatever the original molarity is of the strong acid or base, that's the molarity of the hydronium ion or the hydroxide ion. So in this case, since we started with 0.050 molar of a strong acid, we have 0.050 molar of hydronium ion. So now we can get the pH, which is minus log of the concentration of hydronium. We have a pH of 1.3, which is what we would expect. We're dealing with an acid, HCl, so we expect a low pH. All right, this is a really important concept I'm going to talk about, and one that not very many students end up really grasping. So I want you to really kind of open your ears and take this in. pH simply tells us how much hydronium ion we have in a solution. It really doesn't give us any information at all about whether the hydronium ion concentration came from a strong or a weak acid. So you might have a really acidic solution, real high concentration hydronium ion, and it might have come from a weak acid. Granted, if it's from a weak acid, you would have had to dump a whole bunch of it in to get a lot of H3O, but you cannot with confidence say, just by measuring pH, that it came from a strong acid or a base. That's a really important concept. So in order to have information about the strength of the original acid or base, you have to have Ka or Kb. Let's look at a typical example calculating pH of a strong base. And I specifically picked this one because I want to point out to you that you need to pay attention to stoichiometry. So look for a minute at the ionization of barium hydroxide, which is one of the strong bases. It's a heavy group 2 metal hydroxide. Those are the strong bases, or some of the strong bases. So when it ionizes, pay attention to the stoichiometry or subscripts. There are 2 hydroxides in barium hydroxide, and so make sure you represent that in the ionization. So that means for every 1 barium hydroxide we add to water, we get 2 hydroxide groups. That's important. It's going to change the pH. So the concentration of hydroxide in this case is 2 times the original concentration of the barium hydroxide. In other words, 0.070 molar. So, of course, we're trying to get to pH, but since we have hydroxide concentration, you first have to calculate pOH minus log of that concentration. So the pOH is 1.16, and because pOH and pH have to add together to give us 14, the pH is 12.84. All right, here we go. So now we're getting into the tough calculations in Chapter 15, and that is going to be creating ice tables and equilibrium expressions for weak acids and bases. So I just showed you how finding the pH of a strong acid or base is quite easy because they ionize 100%. If you look at the expression or the reaction for a weak acid or base, you don't have 100% of the ions. You don't really even know exactly how much. Maybe around 99%, maybe 98%. But that's going to affect the degree of ionization affects how much hydronium ion you make. And so it gets a lot more complicated trying to calculate pH of these weak acids and bases. All right, so here we go. Again, here's the generic reaction. And like any weak acid or base, there's an equilibrium established, and therefore there's an equilibrium constant. And you set up the equilibrium constant expression just like you do all the others. It's products over reactants. Okay, remember to leave out water because it is a pure liquid. And so you're going to have to use an ice table in order to determine what the concentration of hydronium ion is. Same thing with a weak base. Look at the chemical reaction or the reaction we show for dissociation of a weak base because it's different than that of a weak acid. When you put a weak base, and they're typically nitrogen-containing neutral compounds, and you put them in water, that weak base is going to snatch a hydrogen ion from water and make the cation form of the weak base and a hydroxide, which is what is left over from the water. So it's a little bit different than the acid. You don't just break it apart. You've got to snatch a hydrogen from water. So pay close attention to that. That's a place for students to get tripped up. And the Kb expression then is the conjugate acid of the original base, concentration of hydroxide, and the only reactant, of course, is the original base. So when you're working with Kb, what you're trying to find is the concentration of hydroxide. So remember that because the problem might actually ask you for pH, which means you've got to convert the hydroxide to hydronium ion before you can get pH. All right, so this is just to give you an idea of some common weak bases. Almost all of them have a nitrogen in, except you've heard of baking soda bicarbonate, hydrogen bicarbonate, or carbonate itself. Those are also weak bases. And the Kb's in all the cases, you can look at how small these values are. That means there's hardly any ionization going on at all. All right, so here's a typical problem. I'm going to start with kind of easier and ramp it up a little bit. Sometimes you can be given the pH of a solution. Formic acid, look at the structure. Okay, that's not one of the 6 strong acids, therefore it's weak. That means ice table. So just get stuck in your head. If you see a weak acid, get prepared to draw up an ice table. So they're giving you the pH, which is 2.38. They want you to calculate Ka. Let's get our problem set up first. It is an acid, so you should start, particularly if it's a free response problem to get full credit, you should start by writing out the dissociation of the acid and water, and that's always formation of a hydronium ion and then the conjugate base of the original acid. From there, you write your expression for the Ka, equilibrium constant, and hydronium ion will always be in the numerator along with the conjugate base, and the original acid will be in the denominator. Leave out water, remember. All right, so now that we have the basic information written, we can set up an ice table. What do we know so far? Well, let me go ahead and write the original reaction up here. Here's the acid we started with. I'm going to write water here even though it doesn't go in the ice table. And we make hydronium ion and the conjugate base of the original acid. All right, so we know the original concentration of the original acid, 0.10 molar. As always, unless you're told otherwise, you assume the initial product concentrations are 0. And do we have any other information than that? Well, they gave us pH. What can we do with that? Well, it turns out if you have pH, you can find the concentration of hydronium ion. Remember the formula? It is 10 raised to the minus pH. The pH they gave us is 2.38. So 10 raised to the minus 2.38 gives us a hydronium ion or hydrogen ion concentration of 4.2 times 10 to the minus 3. pH values are measured at equilibrium. So anytime you're given a pH value, that is an equilibrium value. And look what? So you now have an equilibrium value for the hydronium ion concentration. And because the hydronium ion and the conjugate base are formed in a 1-to-1 ratio, that means that whatever hydronium ion is at equilibrium, that is the same concentration as a conjugate base. So now you have 2 equilibrium values you know. From those, you can figure out the change values for the hydronium ion and the conjugate base. And then, of course, since all of these species are 1-to-1-to-1 stoichiometry, all of the changes are the same. Of course, the original intact acid is decreasing in concentration, so that's a minus, and the products are increasing in concentration. So now we can plug these equilibrium values back into the expression for Ka. And here we go. So here's the concentration hydronium ion. Here's the concentration of the conjugate base. And on the bottom here we have the concentration of the original weak acid. And plugging all those values in, the final Ka value, 1.8 times 10 to the minus 4. Remember that all Kas and Kbs should be much less than 1. If you get one that's more than 1, you did something wrong. Quite often, chemists talk about percent ionization of a weak acid or a weak base. Of course, a strong acid and strong base have 100% ionization. So this measurement only refers to weak acids and weak bases. So that's another formula you need to know. So if you're making a list of formulas, here's another one. Percent ionization, just like percent is always part over whole, and in this case it's talking about ionization. So it's how many hydronium ions, the concentration of hydronium is the part we're talking about, divided by the concentration of the original weak acid or base. And since it's a percent, it's times 100. Here's an example. Let's say that we have a weak acid, and at equilibrium it produces this much of the hydronium ion, 4.2 times 10 to the minus 3 molar. And let's say that our original concentration of formic acid is 0.10 molar. So this is the problem we just did a few slides ago. What would the percent ionization for this weak acid be in water? All right, so the smaller number goes on top, and that's the hydronium ion concentration. The original concentration of the acid on bottom, multiply it by 100, and that tells us that formic acid has a percent ionization of 4.2%. Now this is a slide that after you listen to me describe it, you're probably going to want to pause the video and make sure that you understand it, okay? As I mentioned on the first day of lecture, this chapter is loaded with different types of calculations. So when you finish with the lecture, make sure that you begin to work plenty of problems about weak acids and weak bases, ice tables, percent ionization, etc. So here's a sample problem that asks you to calculate Ka, the equilibrium constant, given the percent ionization. So here's a typical problem. A 0.250 molar solution of a weak acid, hydrofluoric acid, is 3.7% ionized. Find Ka for hydrofluoric acid. So basically, if it says if percent ionized is in there somehow, you want to use the formula for percent ionization. Okay, so remember what that is. It's the concentration of the hydronium ion. I've just gotten lazy here and put hydrogen ion over the concentration of the original weak acid times 100. What information did we get from this problem? Well, let's see. They gave us the concentration of the original weak acid. That goes in the denominator. And we were told that this acid ionizes 3.7%. So this is the information we know. What do we not know from this formula? Well, the only information we don't know is the hydrogen ion concentration. So let's go ahead and simplify this to solve for the hydrogen ion concentration. So let's go ahead and simplify this. First thing I'm going to do is divide both sides by 100. And so then I get, it looks something like this. All right. And now I'm going to multiply both sides by 0.250. And when I do that, I get concentration of hydrogen ion or hydronium ion equals 0.037 times 0.250. And voila, that gives us a concentration of hydronium ion or H plus ion of 0.0092. Honestly, I think there should be a 5 there, but oh well. You get the concept, hopefully. All right, and so since the hydronium ion and the fluoride ion are formed in 1-to-1 stoichiometry, this also equals the concentration of the fluoride ion. Okay, and how do we figure out the concentration of the original weak acid? Now, of course, we need the concentration of this acid at equilibrium. We're trying to calculate Ka, so it requires all equilibrium concentrations. So we know we started with 0.250 molar, but what is there at equilibrium? Well, it's pretty easy. It's 0.250 molar minus however much hydronium ion which is formed, which is minus 0.00925. Okay? So the equilibrium concentration is and I just realized that there's a 0 here that shouldn't be here. So the equilibrium concentration of hydrofluoric acid is 0.241 molar. And so when we plug in all these values, we get that the Ka value is 0.00035, okay, or 3.5 times 10 to the minus 4. Remember that K equilibrium values are unitless. Another way to work this problem, and perhaps an easier way, so it's the same problem up here, but rather than go through the process of plugging into the percent ionization formula, you can realize that if the original weak acid has ionized by 3.7%, that means that 96.3% of the original acid is left at equilibrium. Okay? These two values add up to be 100, of course. And so if the original concentration of the weak acid is 0.250, as they told us, 96.3 times 0.250, of course you've got to put the 96.3 in decimal form, 0.963, is 0.241 molar. That is the equilibrium concentration of the weak acid. 3.7%, again, put it in decimal form, divide by 100 to do that. So multiply 0.037 times the original concentration, and that gives you the equilibrium concentration of the two ions. It's probably an easier way to do it. Okay, get the same value for Ka. All right, these problems are easy to get overwhelmed because there's not just 2 or 3 formulas that you can plug and chug in. So let me give you my thought process on working something like this. It's asking for Ka. So one of the very first things I do is I write at the equilibrium, and then I write the expression for Ka, and that kind of helps me organize my thoughts. So this is a weak acid. This very important that you realize it's a weak acid. A lot of students will tend to see this OH group and think, oh, it's a base. But I want you to see that it's not. So pay close attention because you will see this type of species a lot. Okay? That's called hypochlorous acid. That's what the active ingredient in bleach, by the way. When you put it in water, it is a weak acid. So we will get the hydronium ion as always and the conjugate base, which looks like this, right? So the equilibrium expression for this weak acid all right, and we have been asked in this problem to calculate Ka, which means we need to find the concentrations of the ions, okay? And look at this equation written out. They're present in a 1-to-1 ratio again, so if we find one of them, we automatically have the other. And we can find the hydrogen ion concentration because they gave us pH, and we know we can find hydronium ion concentration from that. So just by writing the reaction that's occurring in the Ka expression, it kind of prompted me to realize what I needed to do. So let's go ahead and find the hydrogen ion concentration from the pH. So the formula we need to know, that you need to remember, is to get the concentration of hydronium ion. Ooh, man, I didn't mean to do that. Okay, the concentration of hydronium ion from pH. Hydronium ion equals 10 raised to the minus pH. And when I plug that into my calculator, what I do is I have to enter the minus 3.91 first and then press the 10 to the Y key. And what I get then is 1.23 times 10 to the minus 4. And that is concentration of hydronium ion. And because of the stoichiometry, it's also the concentration of the conjugate base, which is OCl minus. So let's go ahead and plug this value into our Ka expression. So Ka, again, it's always the concentration of the hydronium ion times concentration of the conjugate base over the concentration of the original weak acid. And so that means we just found out that the concentration of hydronium ion and of the conjugate base is 1.23 times 10 to the minus 4. Since they're both the same, I'm just going to put that squared. what is the concentration of the original acid? It started at, the problem told us the original concentration was 0.50 molar, but we know, again, because the stoichiometry is in a 1:1:1 ratio, the coefficients in the balanced reaction, so we know that this much has ionized, 0.00123. Guess what? This is such a small amount that has ionized that we can neglect it. That's like using the ice table and you can neglect X. And so 0.50, the concentration does not change enough for us to include that. And so that gives us a K value of, let's see, 3.0 times 10 to the, let me count zeros, minus 8. And that's it. But just as a summary, you always want to start by writing a balanced reaction, showing what the weak acid or base does in water, and then you want to write the equilibrium expression for Ka or Kb. The next thing you want to do is calculate the hydrogen ion concentration from the pH, or the hydroxide ion concentration if you're given POH. Whoops, not equals. All right, then typically you would need to use an ice table, and then finally plug the equilibrium concentrations of all the substances back into, that shouldn't be SP, it should be into Ka expression. Now probably the most common mistake on this next exam is a problem like this, where it asks you to calculate the pH of an acid solution, and a lot of people will say, oh, okay, let's see, pH is minus the log concentration of hydronium ion, I'm all set. No, because this is a weak acid, which means you don't know the concentration of hydronium ion. It does not ionize 100%. And so, remember, I'm just reminding you again, anytime you see a weak acid in a problem, you cannot use this formula. You've got to use an ice table. Right, so if you think you know how to work this problem, go ahead and work it out on your own. Now is when you need to start working lots and lots of problems to get comfortable with this. Remember what I told you, though. The first thing you want to do is write the equilibrium expression if you have a weak acid or a weak base. And then you want to write the, you need to write out the balanced reaction, then the equilibrium expression. And they're all going to take kind of the same form, okay? Hydronium ion, conjugate base, over the original weak acid, okay? And in this case, they give you Ka, and they asked you to calculate pH. So when they ask you about pH, they're really asking you for the concentration of hydronium ion. So this is the same type of problem, but they're just giving us different information. So let's go ahead and plug in what we know. And here's the equilibrium expression a little bit less sloppy. So in this case, because we were given Ka, and asked to calculate the equilibrium concentrations, we definitely need an ice table. There's no way around it. So what do we know? We were given the initial concentration of the weak acid. We assume that the products are 0, as always. And so they're all present in 1:1:1 coefficient stoichiometric ratio. So the reactant, as always, is going to decrease by some amount x, and the products are both going to increase by that same amount x. So now we have our equilibrium concentrations in terms of x. We're going to go ahead and neglect x again because Ka is very small. So the rule of thumb, you may remember this from the last chapter, if a K value is less than about 1 times 10 to the minus 3, if it's that or smaller, it's often safe to neglect x. Okay, particularly if the initial concentration is close to 1 or greater than 1, and 0.3 is close to 1. If the original concentration was something like 0.0003, then we could not neglect x, okay? So we're going to cross out that x. That makes it much more simple, and then we're going to plug our equilibrium values back into the expression for K. And here we go. Remember, we were given the value for Ka, and here's our equilibrium values plugged back in. Go ahead and simplify. You start by multiplying both sides by 0.30. All right, 1.8 times 10 to the minus 5 times 0.30 is 5.4 times 10 to the minus 6. That equals x squared, and so let's take the square root of both sides. That tells us that x then is 2.3 times 10 to the minus 3. That is the concentration of hydronium ion. If you go back and read the original problem, it asks us for pH, so we have one more calculation to do. And that is pH equals minus log of 2.3 times 10 to the minus 3. And I know from this exponent that the pH is going to be somewhere around 2 to 3. So I'll go ahead and plug that in. And it turns out that pH equals 2.64. That is our final answer. You try this one, okay? It's really important that you make yourself struggle through and try it on your own. So don't cheat. Do it on your own, and then I'll go through it. So by now you should have tried it on your own. If you didn't, you need to hit the pause button. But as always, the first thing you want to do is write out the equilibrium that occurs between the weak acid and water, hydronium ion and conjugate base, and then the expression for Ka. And they gave us Ka in this problem, and it is 7.2 times 10 to the minus 10. Very small Ka, but that's good. We'll be able to neglect x. Then you want to set up your ice table. I'll rewrite the reaction here. Leave out water because it does not affect the equilibrium. Alrighty, what do we know so far? We know the original concentration of the weak acid. It is 0.025 molar. And of course our product, we don't have any product to begin with. And we're going to use x's again. Okay, the reactant's going to decrease by x, and each product is going to increase by x. Therefore, the equilibrium concentrations are here. And we're going to neglect x. And by the way, on any problem you do in a quiz or test, you have to specifically show or say that you have neglected x. You can't just leave it out and assume, oh yeah, I meant to neglect it. You need to show that you understand it really should be there, but it is safe to neglect. So you can, hopefully this is starting to seem easier to you. Now you want to plug in these equilibrium values to the expression for Ka. So Ka is x squared over 0.025, and again they gave us the Ka value. All right, so x squared equals 7.2 times 10 to the minus 10 times 0.025. And x squared, if you multiply that out, it is teeny tiny. 1.8 times 10, I gotta count zeros again, times 10 to the minus 11. Take the square root of both sides, and the square root of 1.8 times 10 to the minus 11 is a little bit bigger, 4.2 times 10, I gotta count zeros, to the minus 6. That is another common mistake is people solve for x and go, I'm done. Go back and read the question to make sure you are done. What is x, by the way? It is a concentration of hydronium ion. Didn't realize I changed colors. This problem asks for pH, and so we need to, one more step, take the minus log of 4.2 times 10 to the minus 6, and that equals 5.37, a really weak acid. It's not very acidic. All right, this is asking for the percent, not percent, but fraction ionized. And so if you remember, percent ionized was concentration of hydronium ion over concentration of the original weak acid, the original concentration of the original weak acid, times 100. This one is just asking for the fraction, not the percent, so we're going to leave out that times 100. So somehow we have to find the concentration of hydronium ion, and we need to find out the original concentration of the weak acid. Well, we already have the original concentration of the weak acid, okay? That's this. And we just need to find the hydrogen ion concentration. How do we do that? Well, the clue is they gave us Ka. So let's write out the expression for Ka. Okay, there it is. And if you had an ice table, here's the original. It's just like we've been doing the last couple ice tables. The original concentration of the weak acid, 0 ions to begin with. You call this X, Y, Z, whatever you want to call it, but minus X plus Y. Equilibrium concentrations. Is it safe to neglect that Y? Look at Ka, make sure it's small. It is. So we're going to neglect the Y. Then we're going to plug back in for the equilibrium concentration. We're going to solve for Y. And that's going to give us the concentration of hydronium ion, which is what we need to get fraction ionized. All right, so here's plugging everything we know into the equilibrium expression. Simplifying by neglecting the Y. Solving for Y. Okay, and then taking that hydrogen ion concentration, plugging it into the percent ionization formula, and wow, this is not right. All right, so if you were doing the fraction ionized, if it wasn't a percent, that would be right. Okay, that is the fraction. The percent ionization would be that times 100, which is 0.028. Alrighty. Go ahead and try this on your own. Okay, put it on pause and give it a shot yourself. And I'm assuming you can get this answer. If not, go back to the problem I just worked out. It's worked exactly the same way. All right, let's do a couple of samples with weak bases. We work so much with the acids. I don't want you to be stunned when you get a base problem. All right, so the first thing to remember is that the equilibrium for a weak base is quite a bit different. And so refamiliarize yourself. Remember, the weak base has to snatch a proton from water. And so one of the products is always going to be the hydroxide ion. So here's an example. And of course, as usual, the weak bases have a nitrogen ion in it. They give us the Kb value, but you use the same procedure. You write out the equilibrium that occurs in water. You set up your equilibrium expression. So what is Kb? It's the concentration of hydroxide times concentration of, in this case, the conjugate acid, divided by the original weak base. Okay, and they gave us Kb. We're trying to find pH. So if you're working with a base, what measurement is going to give you pH? In this case, it's going to be the hydroxide. And you're going to have to get it, then find POH, and from POH find pH. So there'll be one extra calculation. So the original concentration of the weak base is 0.150 molar. No product yet. Use your minus and plus X or Y. Check to see if you can neglect the minus X or the minus Y. And it is probably okay to neglect it, because remember I said if it's of the order of 10 to the minus 3 or smaller. But the original value is getting kind of small too. It's only 0.1, so it's a little questionable. So I'm going to go ahead and not neglect y in this case, which means you need to solve a quadratic. And then I'm going to show you how to check to see, once you get the value for y, whether or not it would have been safe to neglect. All right, so let's plug in all the values that we have, and we are not going to neglect y right now. And so you're going to start out by cross multiplying and solving for y, which happens to be the concentration of hydroxide. And I'm going to divert for a minute. I want to see if it was safe to neglect y. So our equilibrium concentration of CH3NH2, okay, was 0.150 minus y. So it was, I'm going to write that out, 0.150. What did we just find out y was? 7.91 times 10 to the minus 3. So that's 0.00791. Just going to put zeros in it. And so let's see how much difference that makes. So if I subtract these two, I get that's quite a bit of difference. So if we would have neglected X or Y in this case, then we would have gotten the concentration of the original acid to be 0.150, and what it really was 0.142. So that's probably enough to make a significant difference. So it's probably good we didn't neglect. So it's probably safer to say you can neglect if K is 1 times 10 to the minus 4 or minus 5. Anyway, back to the problem. So now we find the POH. We took the minus log of the OH concentration, found the POH of 2.10. Then we find the pH is 14 minus the POH. So the pH is 11.9. That is a basic solution, which is what we expect. We're working with a base, so it seems like it should be right. Here's one for you to work on your own. It's worked exactly the same way as the one I just did. I will get you started by writing out the equilibrium because this may look funky to you. Okay, it's got a nitrogen in it, it's neutral, therefore it's going to act like a base. Bases always snatch a hydrogen ion from water, and then they end up with a plus charge. And then hydroxide is always the other product. Kb and they give us the Kb value. So you are trying to find pH again, which means you need to find the concentration of hydroxide with an ice table. So go ahead, do that, see what you get. It should be very safe to neglect X in this case because the Kb is of the order of 10 to the minus 8, and we have a little bit more concentrated solution to begin with. So here's your answer. Hopefully you got that. Remember, anytime you're working with a base, you better get a pH greater than 7. Otherwise, you probably, or you did make a calculation error. This has been a really long lecture. I realize that. This is relatively easy. There is a relationship, a mathematical relationship between Ka and Kb. And this is the derivation of it. You do not need to know this, and you're probably brain dead now. If you want to know it, that's great. Hopefully it's easy to follow. But I'm going to skip the next page and show you the bottom line. This is what you need to know. Ka times Kb equals Kw. You remember what Kw was? It's 1 times 10 to the minus 14. So that's kind of another cool relationship. That means that if you know either Ka or Kb, you can find the other one. Here's a simple application of that. They give you Ka, and remember only weak acids and bases have Ka and Kb. They ask you to find Kb, and of course the Kb would have to be for the conjugate base of the original acid. Remember how you get the conjugate base? You just take away a hydrogen ion. Okay, and so how do you get that? Well, Kb is Kw divided by Ka. There you go. Here's another one. Give it a shot. So basically, if you're trying to solve for Ka or Kb, it is always Kw over the other one. Okay, 1 times 10 to the minus 14 over 1.8 times 10 to the minus 9. Voila. That's it, and that is finally it for this very long brain-draining acid and base strength pre-recorded lecture. There's one more, and it will be over determining the acidity or basicity of salts or of ionic compounds dissolved in water. Believe it or not, those little ions, cations and anions, can make an aqueous solution acidic or basic.